Hey guys, Mr. Wood here, and we're back. We're now into chapter 6, so we're going to be working on that for some lessons. And of course, we're at the place where, for you guys, maybe it's time to get ready for the chapter 5 test. But we're going to move into chapter 6, and if you just want to put these aside and come back to them, you can. But here are jokes. Who always goes to bed with their shoes on? A horse. And what is a kangaroo's favorite year? You know this is a leap year. And how much money does a skunk have? 1 cent. 1 cent. There you go. Okay, so we started chapter 6. We said it's on thermochemistry, and we talked about endo and exothermic reactions, very important terms in this chapter. Okay, so here we go. Whoops. Back to where we were in the notes. I'm going to get into some calculations now. Nothing too bad, I don't think. Okay, so this is where we left off. This is actually something that's not on the formula sheet, but it's something that I'm going to have on the test. It's not going to be a major point on the test, but it's going to be on the test. E is equal to the internal energy of a system. It's the ability to do work or produce heat. And what's going to happen here is delta E is going to really equal Q, which is going to equal delta H, is what we're going to say. But let's do this problem. So the key thing here is the sign. So calculate delta H if the reaction is endothermic, so that means delta H is positive. It absorbs 15.6 kilojoules of heat and 1.4 kilojoules of work are done on the system. So if we note that it's done on the system. Okay, so again, this is not on the formula sheet, and but this I will have on the test. So I'm just going to write it right here. So delta E is equal to Q plus W. Well, this one said, they said it was endothermic. Remember, endothermic means delta H is positive. And it says absorbs. So that means the Q is 15.6 kilojoules. And the work is 1.4. And again, the work is done on the system. So it's 1.4 kilojoules. And so if I add this up, what I get is 17.0 kilojoules. And this is positive, meaning that the energy then is going on or into the system. So again, not too difficult a problem, but just adding those two numbers together. Okay, and then to the next page is going to add work to this. Okay, so we just did this problem. Okay, so now the most common type of work done by a chemical reaction is expansion or compression of gases, and we're going to talk about that here. So examples, dynamite blows up. So think about, and I'm going to talk about it in a second, but the volume will take V2 or V final minus V1 or V initial. Well, dynamite blows up. The V2 is much bigger than the V1. So energy is done by the system on the surroundings. A gasoline engine, kind of the same thing. The spark in the engine causes the piston to get larger. So in both of these cases, the work done on the system, what type of work are done in each. So the first one is negative, and the second one, I guess the second one, I can see it could go either way. A gasoline engine, the work though is done by the system on the surroundings. So again, I think it's negative. I think it's negative in both cases. Okay, now here's an equation where it's going to go right in with this, where work is equal to negative P times delta V. And again, this is going to be a small thing on the next test, where P is equal to atmospheres and V is going to be V2 minus V1. And I'll talk about the units here in a second. Well, here it is. So atmosphere liters, where 1 atmosphere liter is 101.3 joules. And I'm going to talk about your formula sheet here in a second. So here's a couple of problems. Okay, so calculate the work done when gas expands from 46 liters to 64 liters. So we're going to do all these here. Okay, so first of all, on the unit, so up here, so I'm going to do it right up here. So work is equal to negative P times delta V. Now the units, pressures in atmospheres, volumes in liters. So the unit we're going to get here is atmosphere liters. Now this is where if we go back to the formula sheet, if we look on the back, the values for R, remember I said R when I talked about the 8.314. And it says it's joules over Kelvin mole. I'll erase this. And I said that a joule is equal to an atmosphere liter. So if we put this in here, an atmosphere liter over Kelvin mole. But then if I look at the numbers, the 8.314 compared to 0.08 and then the 0.0821, which is atmosphere liters over Kelvin mole. And so if I divide those two, so if I take 8.314 over 0.0821, I get 101.3. So this is the number that will, like I said in the notes, this is the number for joules. So if I compare a joule to an atmosphere liter, that's how those compare. Okay, so now to do these problems, and so that might be a good thing to write on your formula sheet, just right down here, is that, just right over here, but that 1 atmosphere liter equals 101.3 joules. That might be a good thing to write down, just right there by the tables for R. Okay, so for letter A, calculate the work done. So work is equal to negative P times delta V. Well, in this case, since the pressure is 0, I have 0 times 64 minus 46. Well, 0 is 0. So this would be 0. And the unit on this, again, technically is atmosphere. And so, and again, what I should, going back up here, I'm sorry, I'm bouncing around. This is the key thing you should know, is 1 atmosphere liter is equal to 101.3 joules. That's what you should know. Okay, now for B. So B, it says that this time the pressure, so work is negative P times delta V. So this time, and it's negative. Sign's important here. So we have 15 atmospheres. And then we have 64 minus 46, and these are liters. So if I do that here, I'm going to get, let's see, 64 minus 46, so 18 times 15 is 270, negative 270 atmosphere liters. And but the thing is, we really want to get this into joules. This is negative, so negative 270 atmosphere liters. So for every, now I'm going back up here. I'm going to go back up here. And for every 1 atmosphere liter, there's 101.3 joules. Gives me negative 27,351 joules to 2 sig figs, negative 27,000 joules. Okay, So just getting these into joules. We're going to do these problems in joules. Okay, and then letter C, is the system in B higher or lower in energy? And the answer is it's lower. And the reason it's lower, it's because it's negative. Remember, exothermic reaction, the delta H is negative, the energy is negative, the energy is going out of the system into the surroundings. Okay, and again, this is not a big point on our next test, but it is definitely a point on our on our next test. Okay, so here's another problem similar to that. Whoops. Sorry about this, having technical problems. Oh gosh. Problem here. Okay, just Mr. Wood and technical problems. Okay, I think we're back now. Sorry about that. I don't even know what happened there. Okay, so delta E is equal to Q plus W, where the total energy by a system is E is equal to Q plus W. So here's another problem. So again, if we remember what work is and what energy is, a balloon is inflated from 2 liters to 4 liters against 1 atmosphere and is warmed by the addition of 200 joules. So we can do work, and then we know the Q, so we can plug this all in. Okay. Sorry about that, Mr. Wood and his technology struggles. Okay, but to do this problem, again, not a major point in the chapter. We're about to start to move into the more major stuff in the chapter, but this, again, will be a small part of this test. So we know that delta E is equal to Q plus W. Okay, and we know that work is equal to negative P times delta V. So I'm going to use both of these. So I'm going to solve for the work. So the pressure, so for work, it's negative 1 ATM. And again, it's V final minus V initial. So here it's going to be 4 minus 2. So what I get is 1 times 2. So what I get here then is 2, it's negative 2 atmosphere liters. Okay, so then I'm going to take that, and I'm going to get this into joules. So for every 1 atmosphere liter, there's 101.3 joules. And this is something that you should know. So I do this. So 2 times 101.3 gives me 202.6. It's negative 202.6 joules. Okay, now I'm going to go to this equation. So now energy is equal to Q plus W. Well, it said for the Q, it said that that 200 joules of heat is added to the system. So the Q is 200 joules plus the W is negative 202.6 joules. So what I get here is negative 2.6 joules, so a real small number. And then it asks, is this system higher or lower? So the answer here would be lower because this is negative. It means energy is being given off by the system. So it's exothermic, so it's lower in energy. Okay, again, not a major point in this chapter, but definitely something that I will put a small amount on our next test on that. Okay, so now we're going to get into really the more major stuff in this chapter. Okay, and this is really, if I talk to anybody that's taken chemistry, this is where they would note this. A measure, or enthalpy is a measure of the amount of energy in a system. I always think it's heat. So delta H is equal to H of the products minus the H of the reactants. And we're going to come back and talk more later. I don't know if you can see me, but on the back of the formula sheet, it's right here. It's called the heat of the reaction. And like we said, exothermic reaction, the heat is lost by the system and the surroundings gain the heat. So in this case, exothermic, the delta H is negative. The system has lost energy. Okay, and then an endothermic reaction is a reaction that absorbs heat from the surroundings. Okay, I messed up again. Gosh. Sorry about that. Okay, so anyways, the endothermic reaction, a reaction that absorbs heat from the surroundings. Often the surroundings immediately around the reaction will become cold. So delta H here is positive. Now delta H can be calculated from several sources, and we're going to go over each one of these. Stoichiometry, that's where we're going to look at a balanced equation, and we're going to have, and we'll have energy in the equation. Calorimetry, where we're going to do SMAT, Q SMAT, SMAT plus CAT. Hess's law is something new, not difficult. From tables, you're going to be given tables where you're going to have energy values and bond energies, which we're going to do in Chapter 8, which we'll probably do next semester, or a combination of these. Okay. So that is a good place to go ahead and stop. Sorry about the technical problems, but that's where we're going to pick up. And again, we'll just be working on these as we go. Guys, have a good day. Get ready for that Chapter 5 test.